Spring is just around the corner, which means that gardening season is too. Suppose that you decide to plant roses in your garden this year, but one of the roses nicks you and you develop a bacterial infection. This was the case for a man in 1940 who later succumbed to the disease because sufficient antibiotics were unavailable to treat his infection. Antibiotics have revolutionized our world, significantly improving both the length and quality of our life. However, pathogenic bacteria are becoming increasingly resistant to even our most potent antibiotics, a threat known as antimicrobial resistance. It is projected that by the year 2050, antimicrobial resistance will claim the lives of 10 million people annually and cost the global economy upwards of $140 trillion. Interestingly, many pathogenic bacteria are known to produce O-acetylated peptidoglycan. Peptidoglycan represents the bacterial cell wall and is essential for cell viability, and suitably is the first target of our innate immune system upon infection. However, through the use of enzymes such as peptidoglycan O-acetyltransferase B, abbreviated here as PAP-B, an acetyl group, shown here as a stop sign, is appended to the bacterial cell wall. And this acts as a steric hindrance, voiding off our innate immune response. This method allows for the persistence of infection and can even lead to downstream pathobiological disease even upon successful treatment of the infection. And of course, this supports the threat of antimicrobial resistance. Inhibiting the ability for PAP-B to function properly would result in a more effective response of our innate immune system. And this would rid both the infection and chances of developing downstream pathobiological disease. My research focuses on just this, with two main approaches. First, by utilizing the 3D structure of PAP-B, as well as known substrates such as peptidoglycan, important residues can be elucidated and characterized. These residues that are required for proper function will be considered in the second step, which aims to inactivate PAP-B by inhibiting the residue's ability to function properly, such as for substrate binding and turnover. To discover inhibitors, a high-throughput screen was utilized to identify common small molecule structures that are able to inhibit PAP-B in vitro. In an iterative process, these structures are currently being manipulated to maximize interactions with the identified functional residues. Results have suggested several molecules that can inhibit not only the action of PAP-B in vitro, but also have the ability to inhibit the growth of pathogenic bacteria in vivo, an important translational step of potential antibiotics. These structures serve as the first known inhibitors of PAP-B and can potentially lead to a novel class of antibiotics for the treatment of a broad range of pathogenic bacteria. I hope that through this work, we will never have to think twice about stopping to smell the roses. Thank you.